We start today's presentation, and that is the part of the chemistry. And fundamental of chemistry is that of the chemical bonding, and the chemical bonding correlates with the atoms present in a molecule or a substance. So, atom itself, that is very smallest particle of any of the substance. Earlier this was concluded that atom was only the smallest particle that cannot be break down. But further, since last century, the development of the atomic structure in which the subparticles are also there, and those subparticles are electrons, protons, and neutrons. So here today we discuss about the how these electrons are responsible for the bonding in the molecule. Two atoms are linked with the energy, the forces by which those two atoms are bonded. So here one of the we can concludes here that different atomic orbitals are present in an atom. Here we see the electronic configuration of different elements. For example, if we have the carbon, electronic configuration of carbon is we can say 1s2, where two electrons are present in one s atomic orbital. Then in second shell, the 2s2. So where the s atomic orbitals are filled with two electrons, and then 2px1 and 2py1. So the carbon having the electronic configuration 1s2, 2s2, 2px1, and 2py1. Now, is the one of the simplest example of carbon is CH4. So in case of the methane, four hydrogens are attached, and these four hydrogens attached to the carbon atom. So carbon itself is tetravalent, but here we can say the electronic configuration is 1s2, 2s2, 2px1, and 2py1. So in case of the second shell, as per the electronic configuration, only two unpaired electrons are there. So if we see that two unpaired electron in carbon is there, but the stable compound and most stable compound is the methane. So how the CH4 is formed? So instead of CH4, there may be the CH2. So this is how we can solve this particular problem. So for that purpose, we need the help of the hybridization of atomic orbitals. So in this particular case, the hybridization of atomic orbital, this is most answer for the chemical bonding. So what happen if suppose we have the CH4, in case of the methane, the four hydrogen, where uh, one electron is present in one s atomic orbital, and that is univalent, monovalent. Monovalent, that is the hydrogen, and carbon is the tetravalent. So how we can say that CH4 is formed? Because the electronic configuration is in case of the second cell is 2s2, 2px1, and 2py1. So how this how we can say that CH4 is the stable compound, and what is the how we can say that the CH4 is formed in between the one carbon and four hydrogen atom. So for that purpose, the chemical theory of bonding established by the Pauling, and in that particular case, the concept of hybridization appears. So, what about the hybridization? This hybridization is a process, whatever the process or the method in which two or more atomic orbital of valence shell of an atom mix each other up to form the same number of identical orbital of equal energy. So here also in case of the atomic structure, the energy is also relevant with the different shells, different subshells, and as well as different atomic orbitals. So that concept, whatever how electrons are filled in an atoms, that was earlier discussed in case of the how electrons are filled in an atom. So let's so the concept mixing of different atomic orbitals, and here the mixing of atomic orbital that particularly leads to the new and having the same energy new atomic orbitals. So those new atomic orbitals are relevant with their energy as well as the shape. Shape is also one of the relevant for the. So here the modification, whatever. Suppose we have to see the shape of one s atomic orbital, that is of the spherical, and shape of p atomic orbitals, that is in the form of the dumbbell shape. So here we can say the spherical 1s atom, 1s or 2s atomic orbital. So in case of the carbon, the second shell 2s atomic orbital that have the two electrons, and the 2px having the one electron and 2py having the one electron, whereas there is also the 2pz atomic orbital. So 2pz atomic orbital has no electron. This is the electronic configuration, and as per the chemical theory of bonding, here the concept relates that that is present in the ground state. But when this in the excited state, one electron from 2s atomic orbital is excited, and because the 2s and 2p both subcells are nearly energy level. So one electron from 2s is excited towards the 2p subcell. In case of the 2p subcell, the three atomic orbitals, and we can say those three atomic orbitals. So now those three atomic orbital of p subcell in case of the methane, the carbon. So here 2s, 2px, 2py, 2pz. So four atomic orbitals are there, and these four atomic orbitals mixed with each other and form a new atomic orbitals. And those are not called the atomic orbitals; they are the hybrid orbitals. So hybridization itself, the mixing of different atomic orbitals. Different atomic orbital, whatever their energy as well as their shape of there. So here, in case of the carbon, this is easily explained in particular of the concept of the hybridization of different atomic orbitals. So the here four different atomic orbitals: 2s spherical, 2px the dumbbell shape atomic orbital, where the axis is at x-axis, 2py dumbbell shape. So dumbbell shape 2py, 2pz also the dumbbell shape. So those three p atomic orbitals are lying are present on their respective axis, the x-axis, the y-axis, and the z-axis. So all these four atomic orbitals mix with each other. Whatever the mixing. mixing of anything. Suppose we have the four vegetables are there, and those four vegetables mixed with each other. Then they mix each other, and their reactions occurs, and a new product, that is the so vegetable combined with the four different vegetables. So similar to that, here when four atomic orbitals undergo the process of the mixing of their, and this mixing is called the process hybridization. So hybridization process, the mixing of different atomic orbital, and gives the same number of orbitals, and which are very new, and they have the specific characteristics as per the earlier atomic orbitals. So here we can say this process is called the hybridization. So now, whatever, first of all, if suppose we have to take one s atomic orbital and one p atomic orbital of carbon. Here the example is the acetylene. So in case of the acetylene, two carbon atom and one triple bond is there. So two carbon atom and one triple bond is there. So carbon triple bond carbon. So how we can explain that this is the triple bond is formed, and that can be explained only because of the acetylene, because of the acetylene's hybrid process. So two carbon atom where each carbon having the one 2s atomic orbital and 2px atomic orbital of each carbon atom. So what happened? Here we can explain the three different types of hybridization. One is the sp type, where one has atomic orbital and p atomic orbitals are mixed with each other. So this is sp hybridization, the first one. The second, sp2 hybridization. So the in case of the sp2, we have the 1s and 2 atomic orbitals are mixed with each other. In case of the sp3 hybridization, where one s atomic orbital mix with two other p atomic orbitals. So this process is the hybridization. sp, where one s atomic orbital combined with 2p atomic orbital. In case of sp2, one 2s atomic orbital and 2p 2 atomic orbitals. So here the electronic configuration we have already discussed about the carbon atom. So let's start with the sp hybrid atomic orbital. In case of the sp, one s one of the 2s atomic orbital of carbon, and this combined with 2px atomic orbital of the carbon. So here where go 2p y and 2p z atomic orbital. In this particular context, the carbon, the ground state, and then excited state. So in case, because carbon is tetravalent, so therefore this have the excited state. So 2px, 2s1, 2px1, 2py1, and 2pz1. Out of these, only 2s atomic orbital and 2px atomic orbital undergo the process of the hybridization, in which these two atomic orbitals, where the shape of 2s is the spherical, where 2px having the dumbbell shape at x-axis. So both atomic orbital mixing with each other. So now what happened? Their shape also disturbed as per the atomic orbitals definition, where the space, that is the space, atomic orbital is the space where maximum probability of finding electron is there. So in a dumbbell shape, px axis, two px atomic orbitals are present. So here both combine with each other, and there uh, the energy is also mixing. So energy of 2s and 2px atomic orbital, and whatever they mix with each other, and they produce two sp hybrid orbitals. And these two sp hybrid orbital in a carbon atom, in a acetylene molecule, in a acetylene gas. So here they form a bond between the two carbon atoms, and that is one carbon sp atomic orbital, 2, and another carbon 2 sp atomic. So what happened? We have to see the molecular formula of acetylene is C2H2. So in that particular context, three triple bond is there. So what happened? One carbon atom combined with another and form the sp hybrid orbital, unpaired electron. In case of the another carbon, sp unpaired electron, and they bond with each other. So therefore, a covalent bond is formed between the two carbon atom, and that is the hybrid orbital sp of one carbon and sp atomic orbital of two carbon. So further, the remaining unhybrid atomic orbitals. So those hybrid orbitals remains in acetylene molecule, and they combine, but the unhybrid orbital form a bond. That is, the pi bonds are there. So two pi bonds are formed by the overlapping, collateral overlapping of atomic orbital, p atomic orbital. So this is the one, the sp type of hybridization, where one of the 2s atomic orbital combined with 2px of 2px atomic orbital, and whatever here the electron uh, um, of 2s and 2px, and those mix those having mixed, those are now present in the new hybrid orbitals, and that is of the 2 sp hybrid orbital. Here we can say, for example, one of the other one, the beryllium. So all of you know about the beryllium electronic configuration, and that electronic configuration states that 1s2, 2s2, 4 electrons are there in case of the beryllium. That is what in the ground state. So what happened? These two beryllium atomic orbitals, and having the electronic configuration 2s1 and 2px1. So this one is the well-known example of sp hybridization. So what happened? Uh, the 2s1 and 2px1 beryllium electronic configuration 1s2, 2s2. But these on the excitation, the electronic configuration of beryllium in the ground state is 1s2, 2s2. But in case of the hybridization, because the ground state electrons are excited because of the a compound is formed. So during the excitation of electron, a new electronic configuration of beryllium appears. And that electronic configuration of beryllium is 1s2, then 2 shell, second shell, 2s1, and then the 2px1. So here in second cell of beryllium, 1s atomic orbital which is spherical in the shape, and 2px atomic orbital that is in the dumbbell shape. So both combine mixing with each other. And what happened? They combine with each other and formation of new energetic, highly energetic orbitals. And the name is changed for those particular atomic orbitals. That is new name of S atomic orbital and px atomic orbitals are changed, and the new name is the sp hybrid orbital. Orbital, atomic orbital are converted into the hybrid orbital. In case of the hybrid orbital, the characters. What about the characters of s atomic orbital and 2px atomic orbital remains there. So that is the character. So how characters of s and p atomic orbitals remain appears in case of the beryllium hydride. So BH2 where the beryllium undergo the process of sp hybridization. So here the molecule beryllium hydride BH2, and this is formed due to the overlapping, whatever the mixing of two orbitals. One of the and those overlapping of sp hybrid orbital with the atomic orbital of two different hydrogen atoms. All of you know the electronic configuration of hydrogen is what? 1s1. One electron is present in hydrogen atom. So that is how we can say the two hydrogen atom combined with beryllium. Beryllium undergo the concept, the mixing of atomic orbital having approximate same energy level and new orbitals. New hybrid orbitals called the sp hybrid orbitals. And those two sp hybrid orbital where one each hybrid orbital having the one electron. In case of the beryllium, the sp hybrid orbital having the unpaired electron, and these unpaired electron when combined with the 1s atomic orbital of two hydrogen atoms. So therefore, stable the H bond beryllium bond hydrogen molecule, and this is the whatever the linear molecule. The diagram here can show the overlapping of atomic orbitals, and here the whatever you can say the yellow and there the green. So this one is the sp orbital is formed. So whatever this can be explained, and so therefore the diagram of it. Now the sp2 hybridization. sp2 hybridization in case of the hydrocarbon, that is in ethylene. Ethylene, two carbon atom and four hydrogen atom. So how the bond is formed? You can say two carbon atom where the tetravalent in nature. So each carbon atom is in a tetravalent. So ethylene C2H4, two carbon, hydrogen 4. So carbon undergo the process of the sp2 hybridization, where one s atomic orbital this mixes with 2px and 2py atomic orbital. So that process is the sp2 hybridization. So whatever one of s atomic orbital and 2p of y atomic 2p of x 2px and 2py, whereas the third one does not undergo the process of the hybridization. So in case of ethylene, the carbon-carbon bond, sigma bond, and then the carbon double bond, this form. So carbon-carbon double bond, where one bond is the sigma and other bond is the pi bond. So that is the concern of the ethylene. So ethylene, the well-known compound in the polymers, that is the polythene. So here, in case of the sp2 hybridization, the energy states of valence electron in an atom of the second period are in 2s and 2p atom. In case of the another beryllium, BCl2, BF2, that is the beryllium. All of you know about the electron configuration. Beryllium atomic number is the 5. So 5 electrons are arranged in different atomic orbital. So underground, whatever the we can say uh, the electronic configuration. So electronic configuration itself is 1s2, 2s2, and 2px1. The beryllium, 5 electrons, and atomic orbital, 3 atomic orbital. In case of the beryllium. So beryllium is the trivalent. So this cannot be explained on the basis of the given electronic configuration of beryllium. Beryllium 5 electron, and this where the 1s2, 2s2, and 2px1. So this cannot be explained that beryllium boron is a trivalent. So here BF3, this is also the example of the sp2 hybrid orbital. So whatever the sp2 hybrid orbital, here the valence electron in an atom of second period where the 2s, okay, and 2p orbitals, they mix with each other and form three different new orbitals, and those three different new orbitals are the sp2 hybrid orbitals. So new orbitals are formed, and those are the sp2. So here we can see the example of the sp2 hybridization. Here three different sp2 hybrid orbitals are present, and the example is the bf3. So in case of the bf3, that is the boron fluoride, boron trifluoride, boron 1s2, 2s2, 2p1. But excitation state, the electronic configuration, that was the ground state. In case of the excited electronic configuration of boron is 1s2, 2s1, unpaired electron, 2px1, unpaired electron, 2py1, unpaired electron. So central atom in BF3, boron trifluoride, boron trichloride, when the central atom makes use of sp2 hybrid orbital, and then compound so form has a trigonal shape. So we can say in case of the sp2 hybridization, the shape is the trigonal. Trigonal, whatever the bond angle 120 degree. So here the three different hybrid orbital of sp2, sp21, sp22, and sp3 third. So these form, that is the compound is itself is the boron trifluoride. Now we can say one another one, and this the third one. This one is the sp3 hybrid orbitals. sp3 hybridization. Here the mixing 1s and all of the three atomic orbital. This produces a set of four equivalent sp3 hybrid orbitals. The four sp3 hybrid orbitals point towards the vertices of a tetrahedron. Here, tetrahedron shape of molecule is formed. Earlier, we get the linear in case of the sp hybridization, the trigonal in case of the sp2, whereas in case of the sp3 hybridization, the tetrahedron shape is formed. So, what about the tetrahedron? The four their bond angle, respective bond angle between the two bonds are also there. So here the concept, and that concept itself is the sp3 hybridization. sp3 hybrid orbitals. So mixing one as all the three atoms produces a set of four equivalent sp3 hybrid orbitals, and these have the same energy and shape of all these four new hybrid orbital is the one. Shape is no difference between any of the four sp3 hybrid orbitals. So we have the hybridization, the mixing of atomic orbital. So the four sp3 hybrid orbital points towards the vertices of the tetrahedron. This can be shown. So this one is the, whatever we can say, the shape of the molecule, and that is, you can say, the methane. Methane, carbon, four hydrogen atom. These four hydrogen atoms combine and form a bond, form a chemical bond, and that bond is between sp3 of carbon with the 1s of hydrogen. So therefore, this specific hybridization itself, the example sp3, and this is in case of the methane. So in case of the methane, the 3 2p atomic orbital of carbon atom are combined with its 2s atomic orbitals to form new atomic orbitals, sp3 hybrid. So new orbitals are formed, and then we have the mixing of these, and that the new dimension, and that dimension having the all four hybrid orbitals in the same direction, same orientation, same energy, and those are the sp3. So here are the some of the questions, and how we can explain whatever we have already discussed: sp3, sp2, sp hybridization. So different state of hybridization, how they can be explained in practically in the chemicals, various chemicals. In case of the, where are the chemicals, and what about the shape, what about the energy, and what about the type of bonding. So here different hybridizations are there, and we can explain one by one, and this is one of the question. And which molecule contain sp hybridized atom? Here, what do we have? HCOOH. The first one, formic acid. HCOOH. This is the formic acid. Methanoic acid. The choice A. So we can, how we can say that Here the sp hybridization hybrid orbitals are present in case of the methanoic acid. First one A, that is HCOOH. So formic acid contain only the uh, carbon double bond oxygen. One bond is there, and then another is the carbon single bond oxygen. So here no chances of the sp hybrid orbitals. In case of the nitric acid, there is no chances of the sp hybridization because fundamentally sp hybridization we have the triple bond. The third one is anyone have the give the name of the third compound? The C, that is the HN2. So this is also nitric acid B and over the nitrous acid. So B is the nitric acid and C is the nitric acid. Here carbon double bond may be appear but not the, so whatever the last one, the D, that is the hydrocyanic acid. So in case of the SCN, the bonding carbon tetravalent and one valency goes to hydrogen and then three valencies combined with the nitrogen atom. So here carbon triple bond nitrogen is there. So cyanide group HCN hydrocyanic acid. So carbon triple bond nitrogen. So here the answer is this one. Now we have another example sp2 hybrid. Which species contains an sp2 hybridized orbital? Here let's we have the periodic table, then sp2 hybridization as we have earlier discussed. So sp hybridization is that in which one s and one p atomic orbital undergo the mixing, and here we want the sp2 hybridization. So the effect is there in case of the sp2 hybridization, one of the s and 2p x, 2p atomic. So here sp2 hybridization, whatever we already discussed about the option number A, that is the beryllium hydride. So in case of the BeH2, sp2 hybridization is not. So BH3 having the sp3 hybridization. BH3 having the sp2 hybridization. So the answer, correct answer is the BH3. So whatever the ammonia, then the H2O plus hydrogen ion. So therefore, this is the sp2 hybridization. So whatever we can say, this is the answer for that, and this can easily explain whatever what is the hybridization, mixing of it. Easily explain, but that answer comes and take 50 years for the answer. So correctly, the atomic orbital undergo the process of mixing. The natural phenomena, whatever, this is not the artificial one. So with the help of the natural phenomena, this one, we get the answers for many of the questions. This is the present one. So here in the case, which species contain an sp2 hybrid atom? BH2 only two bond, BH3 3, and we have already discussed. So this have the sp2. In case of ammonia, this is sp3. Sp3 itself is the whatever, this one is called the tetrahedral hybridization. 4. In case of the S3O plus, this is not. So therefore, we have already seen that is the answer. Now the another question: can equivalent bonds in the Lewis structure of propane will account? for how many valence electrons. So what do we mean by the valence? Here, the hybridization propane. What is the propane? Three carbon atom, long hydrocarbon, CH3, CH2, and CH3. So how many valence electrons? All of you well known about the carbon, where the excited state, the four electrons are present. So 10 covalent bond in the Lewis structure of propane will account how many valence electrons. So for that purpose, if you see the carbon having the 4 electron and paired electron, so this here the carbon and hydrogen. So here the propane. So in case of the propane, 3 carbon atoms are there, and 1, 2, 3 carbon atom, and then tetravalency of carbon atom can be filled with uh, the 4 different. So here uh, the carbon, 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 sp3 hybridization, the number of participant electrons, and those are the 20. So how we get? Because of the valence electron. Here another one, whatever the electro energy difference, because the covalent compounds and covalent compounds, the covalent bond and covalent bond is the simple definition, and those are the whatever the covalent bond, pairing of electron, and then bond is formed. So in case of the covalent bonding, covalent compounds, other factors are also involved by which the new characteristics appears. For example, if we have the one of the group chalcogenides, that is the group of oxygen, so oxygen sulfur, okay, oxygen group, oxygen then sulfur, oxygen having the electronic configuration 1s2 2s2 p 2 8. So what we have 8 electrons in case of the sulfur, that is the other thing. Now H2O and H2S, major difference. So this is why, because the other characteristics, the property of atomic atoms are also involved. That is electronegativity. So electronegativity, the force by which the paired electron between two atoms are forced towards there. So here the electronegativity, whatever the electronegativity, the electron pair attraction in a bonding, in a bond by the, and that property is called the electronegativity. So here we can see the difference between the covalently bonded atom is less than 0, less than 0 to 0.3. The correct answer is the B, 0 to 0.3. So this is because of the electronegativity. Whatever we are coming here the hybridization. So hybridization, the mixing of atomic orbital and the nu is given. Then totally other factor, the electronegativity, that is also important. So here the correct answer is 0 to 0.3. One more example. Which among the following on closed? This one is also related with the hybridization, the ethers, carbon, oxygen, carbon. The hydroxyl groups, whatever hydroxyl groups are attached, then the carbonyl compound, and then the carboxylic acids. So here answer is the ether. So ether is having the sp3, have one more is there. What is the hybridization of sulfur in H2S? Hydrogen sulfide, whatever we have discussed. So here also similar to the water, answer is the sp3 hybridization, where one of s atomic orbital and 3 of p atomic orbital combined. So here in case of here the three different electronic hybridization process is involved. So answer is 1s and 3 of d. So let's last one. When we draw a double or triple bond between two atoms, we imply that either 4 or 6 electrons are directly between these two atoms, and that is the hybridization. Since this is impossible, we must have the extra electrons off to the side, in which we refer to as a pi bond. So pi bond itself is formed. So this is, we can summarize different atomic orbital where the shape, where the energy that undergo the process of the hybridization. So let's only three different hybridization: sp3, sp2, and sp hybridization. So here the state of hybridization and new hybrid orbitals are formed. And this is very important and this for explaining the different difficulties appears during the research work. So all of you are uh, given, that is the present information hybridization of atomic orbitals. This is most urgent need. Substitute, that is the substitute all those earlier different concepts are given, and this is the modern one, modern periodic table, and where this was explained. This is the hybridization process. So all of you are welcome to get any more queries that all of you have to ask, and ask me directly or indirectly, whatever you can see, write to mail or indirectly. So this is all about today's the most important, and that is what we have that particular related to the hybridization. And hybridization is the mixing of atoms.